Okay, let's continue our conversation in 12.4 about the 68, 95, 99, 7 rule. We did a few examples in the last few videos where if we found out we had exactly one standard deviation away from the mean, about 68% of people fell in that category. And if we have exactly two standard deviations away from the mean, 95% of the people fell in that category. And if there was exactly 3 standard deviations, then 99.7% of people fall in that category. But what happens if our numbers aren't exactly 1 away, or exactly 2 away, or exactly 3 away? Well, then we can't really always rely on that 68, 99, 95, 99, 7 rule if that's not the case. And so what we might have to do is we might have to calculate how many standard deviations away our value is. It might not be exactly 1, 2, or 3. It might be at a different value. So what we want to do is we want to calculate that value, and it's called a z-score. We want to be able to find exactly how many standard deviations away our value is from the mean by finding the z-score. That means we're going to use this formula where we take the data item, we subtract the mean, and we divide by the standard deviation. So we know how many standard deviations away we are from the mean. Positive numbers would mean we are above the mean, and negative numbers means we would be below the mean by that amount. So, looking at example number 4, it says the mean weight of a newborn infant is 7 pounds and the standard deviation is 0.8 pounds. The weight of newborn infants are normally distributed, so it follows that bell curve, and we want to find the z-score, or how many standard deviations, for a weight of a 9-pound baby, a 7-pound baby, and a 6-pound baby. So, we could draw the chart, but if the chart isn't exactly 1 or exactly 2 or exactly 3, then we aren't able to follow that 68, 95, 99, 7 rule. So let's go ahead and use our z-score formula to figure out how many standard deviations away each of these values are. So on the first one, we're going to take the 9, our data item, we're going to subtract our mean, which is 7, and we're going to divide by our standard deviation, which is 0.8. I ended up getting 2.5. What that means is that if you have a 9-pound baby, then that means it is 2.5 standard deviations above average. It's 2.5 standard deviations above an average pound newborn. If you had a 7-pound baby, we could figure out what his z-score is. We can take our 7, we could subtract our mean, and we can divide by our standard deviation of 0.8. Didn't you get 0? So what does that mean? Well, doesn't that mean that he's 0 standard deviations away from the mean? He's exactly at the mean, and so he's not above, he's not below average, he's exactly at the average newborn weight. But what happens if I have a 6-pound baby? We know that's a little bit below average, right? And so let's see what happens here. If we take that 6, if we subtract our mean, and we divide by 0.8, so this is why it's important to keep it in this order, we end up getting a negative 1.25. So what that means is really, if I have a 6-pound baby, then he or she is 1.25 standard deviations below the mean. If you were doing a bell curve and the mean was here, your baby wouldn't be 1 below, but he'd be a little bit lower than that. He'd be 1.25 standard deviations below the mean. The farther down it gets, you've got to be concerned. Or if your baby was way up here, you would be concerned. But we kind of compare weights of newborn babies to make sure that they kind of fall in the quote-unquote normal category. Okay? And we can find exactly where his z-score lies by using that formula. Let's do another one. If you look at example number 5, this one is talking about 2 different tests, an arithmetic test and a vocabulary test. It says here that a student scored a 70 on an arithmetic test and a 66 on the vocabulary test. Now a 70 sounds higher than a 66, but is it really better? It says here the scores for both tests are normally distributed. The arithmetic test has a mean of 60 and a standard deviation of 20. The vocabulary test has a mean of 60 and a standard deviation of 2. On which test did the students score better? Well, what they're really asking for is, compared to the average, how much better do they score on the arithmetic test and how much better did they score on the vocabulary test? If I'm 1 standard deviation away from the mean, above the mean, that's a little bit better than 0. Or if I'm 2 standard deviations away from the mean, above the mean, that's better than being 1 standard deviation above, right? And so what we want to do is we want to find what standard deviation they fall at. So let's go ahead and compute their z-score. Let's figure out where they fall. And so if I'm taking the arithmetic test and my score is 70, I have a mean of 60 and a standard deviation of 20, I can use my z-score formula to figure out that I fall 0.5 standard deviations above the mean. I'm a little bit above average, right? On the vocabulary test though, I scored a 66, the mean was 60, and my standard deviation was 2. So using my formula, I ended up getting a 3 for my z-score. What that means is I'm 3 standard deviations above the mean. If I was looking at a chart and my 60, my average was here, on the arithmetic test, I was 0.5, I was here. But on the vocabulary test, I was not only 1 standard deviation, 2 standard deviations, but I was 3 standard deviations above the mean. I was here. Which test then did I really score better on, even though 70 sounded higher than a 60? Didn't I score way more on the vocabulary compared to the average person? And so I would have said that I did better on the vocabulary test than the arithmetic test by comparing my z-scores.